Hello, so in this video we'll be talking about energy. Alright, so what is energy? As you can see here we have energy. Energy can be kinetic or it can be potential. And then if it's potential, then we can have different forms of potential energy. Or we can have different forms of kinetic energy. And as we continue through this semester, we'll be talking about all these different forms and how these things affect energy. But what we're going to really be focusing on today is transfer of energy and the law of conservation of energy. So the question is, what is energy? That's the question we're trying to figure out from now. So what is energy? Energy is basically, so energy is the capacity or ability to do work. So whether it's through photosynthesis, or this guy is pulling on a car trying to be the world's strongest man. Energize a bunny that keeps going and going and going. We're still all talking about energy. So again, energy is the capacity or the ability to do work. Without energy, then we cannot do work. Work cannot be done. So the law of conservation of energy, just like the law of conservation of mass, energy is neither created nor destroyed, but it's going to be converted from one form to another. And we have two types of energy. We have kinetic energy, which is energy due to the motion of the object, and we have potential energy, which is due to position, or sometimes we say stored energy. So let's look at this diagram here, for example. At the foot of the hill, the cyclist has 100% kinetic energy. And as he moves up, that kinetic energy is transferred to potential energy. So here he would have 100% potential energy. So the energy as he goes up and is transferred as he comes down again. So he goes from 100% kinetic energy at the bottom to 100% potential energy at the top, and 100% kinetic energy at the bottom again, because energy is being transferred from one form to another. So we're going from kinetic decreases as he goes up until it reaches to 0 at this point, and as he comes back down, potential decreases and kinetic increases until kinetic comes back to 100% at the bottom. Now, how do we measure energy? All forms of energy are measured in units of joules. So this is what we call the SI unit. Alright? So this is a standard unit of measuring energy. But energy can also be measured with other units. So think about a calorie. Calorie, or sometimes I call it the small cal, as someone said in class today, the skinny cal, and we'll see why in a bit, is the amount of energy required to raise the temperature of water by 1 degree Celsius. Whereas the big cal, or the fat cal as somebody said, is nutritional energy. So think about eating, think about carbs. That's what we're talking about when we're mentioning the big cal, and that is the one with the capital C. Then you also have the kilowatt hour, which is seen on electric bills. Ask your parents to see their electric bills. They'll show you it comes in kilowatt hour. That tells you how much energy you consumed within that month in kilowatt hour. Okay, so now we're going to do some conversions. Alright, so we're given a question here where we're told a candy bar contains 225 calories of nutritional energy. How many joules does it contain? So first we look at what we're given in the question. And we're given 225 calories. So that's what we're given, 225 calories. And that's the big cal. And we want to find joules. So how do we go from there? So we start with now look at your conversion factor. There is no direct conversion between. So we start with the big cal. We need to go to small cal, and then from the small cal we can go to joules. So that's how we're going to set it up. Big cal to small cal, and small cal to joules. So we start with our given in the top left hand corner for our dimensional analysis. That's 225 cal, big cal. We want to convert it to small cal. That looks too big. So 1,000 small cal in 1 big cal. Then we want to convert that to joules. So that's 4.184 joules, 1 small cal. And again, let's look at how our units come into play. Big cal, they cancel each other. Small cal, we're left with joules. So we multiply out, and our answer 9.41 by 10 to the 5th joules. Alright, so let's look at another example now. The complete combustion of a small wooden match produces approximately 512 calories of heat. How many kilojoules are produced? So again, we look for what we're given. 512 calories, and this time is a small cal. So we're given 512 calories, and we want to find kilojoules. And that K needs to be small. So where do we start? We start with our small cal. We go to joules. And then from joules we go to kilojoules. So let's set up our dimensional analysis. We start with 512 cal. We want to convert that to joules, so we know that there are 4.184 joules in 1 cal, and that's a small cal. Then we want to convert joules to kilojoules now. In 1 kilojoule we have 1,000 joules. So again, let's look at how our units play out. Cal cancels with cal. Joules cancel with joules. We're left with kilojoules. And our final answer is 2.14 kilojoules. Remember, you multiply and then you're going to divide by 1,000. And that will give you your answer. Okay, our third example. An energy bill indicates that the consumer used 955 kilowatt hour in July. How many joules did the consumer use? So we look at what we're given. 955 kilowatt hour. We want to find joules. So we set up our unit conversion chart. we want to start with kilowatt hour, and we go to joules. So that's 955 kilowatt hour. So that's what we start with. We want to convert that to joules. So that means we need to divide by kilowatt hour. We know that there from here, using this conversion factor here, 3.60 times 10 to the 6th joules in 1 kilowatt hour. So you multiply by this, and you would write your answer in scientific notation. Don't forget that, because you would get a very large number. You should get this in your calculator: 3.438 times 10 to the 9 joules. But since we only started here with 3 significant figures, we need to give our answer to 3 significant figures. So our third significant digit will be this 3. Since the number after 3 is greater than 5, then the 3 needs to increase by 1. So our answer now becomes 3.44 by 10 to the 9 joules. Okay, and that tells us our answer is given to 3 sig figs, because that's what we rounded it off to. Okay. Okay. So during a chemical or a physical change, energy can either be absorbed. That means energy is taken in, or it can be released. So it's either absorbed or released. So let's look at what happens here on these diagrams. So these are called energy diagrams. Okay? And it shows us the energy change that occurs. Remember, the substances we start with, they're called reactants. Whatever we end with, they're called products. Here we see that the reactants have more energy than our products. So that means heat was released, because they had to give off energy to get down to this level. And when that happens, we call this an exothermic reaction, because heat is released. Whereas in this one, the reactants have less energy than our products. So energy had to be absorbed, or heat was absorbed to go from reactants to products. And that we call an endothermic reaction. One thing we have to be careful with here is this is in terms of energy. So in an exothermic reaction, the products have less energy than the reactants. In an endothermic reaction, the products have more energy. And again, the key word here is energy. Okay, so here now is a demonstration that I did in class, and I have some results that we got. Dissolved approximately 2 grams of each of the following substances in approximately 100 milliliters of water. We dissolved sodium hydroxide first. The initial temperature of the water was 21.5 degrees Celsius. And after mixing the sodium hydroxide into it and dissolving the sodium hydroxide, it increased to about 26.4 degrees Celsius. So if we find the temperature change, that is the difference between these two, so that would be 26.4 minus 21.5. That gives us temperature change of 4.9. Whereas with potassium chloride, we had 22.3 degrees Celsius initially, and we went to 19.5. So our temperature change was If we take 19.5 and we subtract 22.3 from that, okay, so that will give us our temperature change. That's a negative 2.8. So here, with the sodium hydroxide, we saw that the temperature increased, whereas with potassium chloride, the temperature decreased. Now, in the containers, when you felt the containers, this one felt hot or warm, whereas this one felt cold. So what that tells us is that heat was released. And here, heat was absorbed. So if heat was released, then that tells us that this reaction with sodium hydroxide is exothermic, because it produces energy. It gives off energy. The reaction gives off energy. It releases energy. With potassium chloride, since it got cold, the temperature decreased. That means heat was absorbed. Energy was absorbed. So this one is endo. When you have changes occurring that absorb energy, the process will always be endothermic. Changes, physical or chemical, that occur that release energy, they're referred to as exothermic reaction. And remember, these changes can either be physical or chemical. Right? And you have some examples on your note sheet that you have some changes that you have to classify as endothermic or exothermic. So go ahead, you can pause the video here, go ahead and see if you can classify those. Once you're done, play the video again and I'll give you the explanations and the answers. Okay, so you should be finished with those. Now let's see. Wood burning in a fireplace, that it releases heat, so that makes it exothermic. Now ice melting is a tricky one, because remember, the temperature of the ice is doing what? Increasing, but it has to absorb energy. Alright, so it has to absorb energy in the form of heat to melt, because it's getting warmer. How does it get warmer? It has to absorb the energy, so that makes it an endothermic reaction. Water freezing is the opposite to ice melting. It has to release heat because it gets cooler, so that is exothermic. Natural gas burning, just like we did with the wood burning, it releases heat. So that makes it exothermic. Now let's go to the ice melting and water freezing a bit. It goes back to when we talk about the states of matter: solids, liquids, and gases. Remember, solids have the least energy, or better yet, let's use least. They have the least motion and most motion. So that means when we talk about motion here, motion refers to energy. So if you're going from solid to liquid, like in ice melting, so that's melting, it goes from low energy to high energy. How does it get that energy? It has to absorb energy. The particles themselves have to absorb energy. Whereas when you go from a liquid to solid, You're going from high to low. So you want to decrease energy. So you have to release that energy. So that's how you give off the energy, and that's why it's exothermic reaction. As we talked about when we did the states of matter, the particles in a substance are constantly in motion. So these particles will just be moving from point to point to point. That's if they're in a gas. They will just move randomly. Whereas in liquid, their movement is more ordered. So they have a fixed, so they're more ordered. Whereas in solids, they can only go from one point back and forth. So gases, particles in gases, liquids or solids, they're always going to be moving. So that's why they're in constant motion. If they're in constant motion, then they're going to have kinetic energy. Now, how can we measure the motion of these particles? We cannot measure each individual particle, how it moves. What we're going to do is measure their collective motion. And we're going to do this by measuring their temperature. So that means temperature is related to kinetic energy. And we know kinetic energy is related to motion. What that tells us is that the average kinetic energy of the particles in any system is the temperature. It's a measure of the temperature. So temperature gives us an indication of how fast these particles in a substance is moving. Now, if the particles are moving fast, then you're going to have higher temperature. And this was an animation we had in the PowerPoint. And you can see these particles moving at different speeds. Some would move slow, and some would move really fast. But the temperature is the average kinetic energy. So it's not just one particle, it's all these particles. The average kinetic energy of all these particles. That is what will give us the temperature of the substance. Now, when we make chemicals, or chemical bonds are formed, energy is required to form these bonds. And that chemical energy, or that energy, is stored in these bonds here. That is what links the individual atoms together. So the energy is stored in these bonds. And it's called chemical energy because it's in a chemical bond. And because it's stored energy, it is a form of potential energy. So again, whenever we create bonds, energy is absorbed. It requires energy. The energy is stored in the chemical bond. So all these bonds here will store the energy. So there'll be some energy between these bonds. And because it's stored energy, it is a form of potential energy. Since the particles that make up a substance possesses both kinetic and potential energy, the sum of the kinetic and potential energy gives us thermal energy. What is thermal energy? It's just the sum of the kinetic energy and the potential energy of the particles in a system. When thermal energy is transferred from one object to another, it is called heat. Now, it is important that we note here, hot or cold is only a relative something. It's a relative feeling. It's a feeling based on what one person identifies as being hot or cold. When we talk about thermal energy, we talk about heat. Heat is the only thing that is transferred. If you touch something and it feels hot, that is because the heat is not hot. Heat is you're absorbing heat from the substance. Thermal energy is transferred from the object to you. That's why it's hot. If something feels cold, you are transferring thermal energy. So heat is lost by, let's say, you. Alright? So if you touch something and it feels cold, that means you're transferring thermal energy from your body to that object. So you're losing heat. That's why you feel cold. So again, hot or cold is just a perception. It's just a feeling. It is relative to each individual. The only thing we can directly measure is heat, the transfer of thermal energy. When measuring the amount of heat transferred, we need to know two things: the substance and its heat capacity. But what does that mean? Each substance will have a different heat capacity. And as we see here, the heat capacity is how much energy is required to change the temperature of a given substance by, or of a given amount of a substance by 1 degree Celsius. Now, when we say this, we need to be careful. We can cause an increase or a decrease by 1 degree Celsius. If we go to increase, that means it must absorb energy. If it decreases, then it must release energy. And then that's an R. Now, specific heat is the temperature required to change 1 gram of a substance. Sorry, not the temperature, but the thermal energy required to change the temperature of 1 gram of a substance by 1 degree Celsius. And it's measured in joules. So the thermal energy required to change per gram per degree Celsius. So this is the unit of specific heat capacity. You need to be familiar with these definitions. Make sure you understand the difference between heat capacity, specific heat capacity, and you need to be able to identify specific heat capacity based on the units. Okay, so here I want you to look at the specific heat capacity of some common substances. We have lead, gold, silver, copper, iron, aluminum, ethanol, water. So if we have 1 gram of any of these substances, this tells us how much thermal energy we need to change that temperature by 1 degree Celsius. Now look at the value for water. It's very high. Water has a very high specific heat capacity. That means it takes a large amount of energy to change or to increase the temperature of water by 1 degree Celsius. So here's a concept check. The ice in a cooler packed with cool drinks lasts much longer than the ice in a cooler packed with warm drinks. Can you explain why this happens? Okay, we will not discuss it in this video, but we will discuss it in class next time we meet. Okay, so think about it. I'll give you some hints now. Think about it. In California, San Francisco is a coastal city, whereas Sacramento is an inland city. On any given day, these two cities receive the same amount of sunlight in terms of the intensity of the heat that they receive. But in San Francisco, and I'll shorten it by San Fran, the temperature could be about 75 degrees, about 75 Fahrenheit, whereas in Sacramento, it could be about 100 degrees Fahrenheit. Why the drastic difference? This is coastal. You can't spell coastal. Don't laugh. Alright, so this is a coastal city and this is inland. So the difference here is that San Francisco has water around it. So the water absorbs a large amount of the sunlight, the energy from the sunlight. So San Francisco is not as hot as the inland city of Sacramento. So think about this when you're thinking of an explanation to answer your concept check. And we'll talk about the concept check when we meet next time in class. So, how do we calculate the amount of heat gained or lost, or the heat transferred during a reaction, whether it's a chemical reaction or a physical change? We do this by using this equation. Heat gained or lost is equal to the mass times your specific heat times your change in temperature. And it is important that we understand what these means. So this is our worded equation. This is our equation in algebraic form. And this tells us what each variable in the equation represents. So Q, amount of heat in joules. So heat is measured in joules. M is the mass of the substance in grams. So how much of the substance do we have? It is measured in grams. Specific heat, which will be a constant for each substance. Okay, and we talked about the unit joules per gram per degree Celsius. Delta. So this triangle is pronounced delta. And what it means is change in temperature. And we always do T final, or sometimes we say T2 minus T1 to get the change. Now the mass, specific heat, these are always going to be positive values. Now the delta T could be positive, right? When it's positive, that means T2 is greater than T1. When it's negative, T2 is less than T1. Whenever it's positive, that tells us heat was gained. The Q, the value of Q, will also be positive. If delta T is negative, that means heat was lost, and Q will also have a negative value. So we're going to go on to look at some examples of when we use this equation to calculate thermal energy lost or heat gained or lost. So in this first example, we have a piece of iron shown below. It underwent the temperature change shown to the right. So this is our temperature change here. We have our initial temperature and our final temperature. We're given the specific heat, and we want to calculate the change in thermal energy. And we also want to decide if heat was gained or lost. So we look at the triple beam balance and we determine what our mass is. 100, that's 120 and 1, so 100, 121 grams. Then we can calculate delta T, change in temperature, because our final temperature was approximately 120 degrees Celsius minus our initial temperature, which is approximately 100 degrees Celsius. And that gives us 20 degrees Celsius. So we know Q is equal to MC delta T. So we go ahead and substitute our values. M is 121 grams. We multiplying that by C, specific heat, which is given to us in the question, 0.450 joules per gram degree Celsius, multiplied by the temperature change, which is 20 degrees Celsius. So we multiply all these values and we get 1089 joules, 1089 joules. But since we only had, yes, and here we go, sig figs, 2 sig figs from our subtraction, we need to round this out to 2 sig figs. So we need to round it off here. The number after our second significant figure is greater than 5. So the 0 needs to increase by 1. 1, 1. Now we cannot leave these values out because we will change the original value of the number. We want to keep the same place value. So we need to add our 2 zeros, so 1100 joules. And that's because we rounded off to 2 sig figs. So in our second example, it says Mr. Courtney heated 235 grams of water from 25 degrees Celsius to 100 degrees Celsius to make a cup of tea. How much thermal energy was used to heat the water? And we're given the specific heat of water. So we need to look at all the information that we're given in this question. We're given the specific heat capacity, we're given temperature, and we're given mass. So we're given mass is 235 grams. The initial temperature, T1, is 25 degrees Celsius. Our final temperature, T2, is equal to 100 degrees Celsius. And we want to find the thermal energy. So to find the thermal energy, we need to start by calculating our change in temperature, delta T, which is T2 minus T1. And guys, when you're working these problems, the ones you're going to have to do on your own, I want you to take your time and set the problem up same way I'm doing it. This will save you a lot. And remember, you will lose points if you do not show your work. Okay? So make sure you take your time and set it up. It will help you to understand the problems much better as you solve them. So we take T2 100 degrees Celsius minus 25 degrees Celsius. So that gives us 75 degrees Celsius. So now we can solve for Q. Q is equal to MC delta T. Notice I'm writing my equations still. I'm showing what I'm calculating. So here I know I'm calculating Q. M, the mass is 235 grams. Multiplied by the specific heat, 4.184 joules per gram degree Celsius. And we multiply by the temperature change, which is 75 degrees Celsius. And again, if we want to look at conversion, units, grams cancel with grams, Celsius cancels with Celsius, so all we left with is joules. So when we multiply this out, we get 73,743 joules. So that's what you should get. If you didn't get that, then double check your calculation. Now let's talk about sig figs. We only need 2 sig figs. So we need to round this number off right there. So that becomes 7, 4. And we went through the explanation as to why that 3 becomes a 4 in it before. Then we need to add 3 zeros as placeholders. And that's in joules, and we round it off to 2 sig figs. Okay, so you're going to have some problems that you're going to work on. The answers are given at the bottom of the sheet in random order, and you're going to have to complete these, and we'll discuss these next time in class. If you have any problems, we'll go over them, any of the questions you had problems with, but you're expected to complete them at home. So to complete this lesson, we're going to briefly review transmitting heat through objects. Now, you've done this before. You've done this in middle school, you've done this in elementary, and you know these stuff, but you may have forgotten them. Remember, there are 3 methods of heat transfer. Alright, and we're going to review these now. So whenever heat passes through a solid, it does so by the process of conduction. And that is because these particles will bump into each other. And if we had the animation, you'd see these particles moving, and they're going to bump into each other. Every time they bump into each other, they're going to transfer energy. So for conduction to occur, there must be some direct contact between the objects. If there's no direct contact, then conduction does not occur. So for conduction to occur, there must be direct contact. Now, how do heat pass through fluids? We talked about this when we did the states of matter. Fluids are, and hopefully you remember these, fluids are liquids and gases. And the process by which heat flows through a fluid or passes through a fluid is called convection. And that is because heat, not heat, but these particles are able to float, so they can move. And if you, what you would have seen with these animation is that this would have been moving, this would have been moving, so they'll be constantly moving, constantly moving, constantly moving. So if this one has energy, it will take that energy and transfer it over here. This one has energy, it will take that energy and transfer it over here. So they're going to flow. That's how they transfer energy, via convection. Sorry. Now, as you heat substances, all right, the particles are going to absorb energy. They're going to move faster. That comma should not be there. They're going to move faster. They're going to travel farther apart and run into each other more often. So this is what it would look like initially. And as the temperature goes from low, you can't see it because this was an animation, but it goes from, let's say, here, and as it increases, these particles will start to move faster. They move apart. Okay, so they'll move apart. And eventually, they'll look like this. So the distance between them will increase. So that causes the substance to expand. Once the substance expands, all right, substance will become less dense. Why does it become less dense? Remember, density is mass divided by volume. We're not changing the mass, we're changing the volume. So think about it, the mass stays the same. If initially, let's say the volume was 1, then we increase, after we heated it, the volume increased to 2. So the same mass divided by 2, this is going to be greater. Initial density will be greater. So it changes, it makes it less dense. Okay? Because we're increasing the volume of the same mass. Alright, so as the substances are cooled, the particles will lose energy. They will contract. So they go from being far apart to close together. Once they get close together, as the temperature decreases now, they're going to become more dense. So this constant heating and cooling of a fluid in a system produces what is called a convection current. And if we look at this diagram here, this is what happens. The cool air here is heated. It becomes less dense. Alright. So here it is less dense. So it loses heat to the window. It becomes more dense. So when it becomes more dense, it sinks. And again, it's going to be heated. It's warmed. It becomes less dense. So it rises. And that process will continue over and over again. It's the same principle that we use to heat and cool homes by a convection current. It's the same principle you see happening in a lava lamp. When the solid at the bottom starts rising, it comes to the top because it's heated, becomes less dense. When it gets to the top, it's cooled, it becomes more dense, and it will sink again. So that's what we use convection. That's how convection current operates. Now, whenever two objects are not touching, and the key word here is not touching, keywords, heat is transferred through a process called radiation. So it's transferred through a process called radiation. So that's how we get energy from the sun, from a fire, because we can't touch the fire, but we feel the heat from a fire radiation. So what is radiation? It's a form of electromagnetic waves that can pass through vacuums. That is where there is, when we talk about the vacuum, there is no matter. So radiation does not require matter for it to be transferred. Okay, so all the energy we get from the sun is via radiation. The hotter the object, the more radiation it will emit. Okay, and when we go into the Bohr model and all those things, we'll talk about electromagnetic waves and so later on. But for now, we just need to know what radiation is, and that radiation, right? Radiation is transfer of heat through electromagnetic waves. Okay, so work on the problems on heat gained or lost, answer them properly, make sure you show your work. The answers again are given in random order at the bottom, back and front. So as you get your answers checked, the answers should be there. Also, take your time, look at your significant figures. Right, and once you finish those, we will discuss them in class next time. And you will have a quiz over the material in this. So you are responsible for knowing your definitions, knowing your formula, the units, and all these things. Make sure you take the time to know them. You will have a quiz over this. Okay? Alright, so hope y'all have a good one. Bless, and I'll see y'all soon. Blessed.